Okay, guys, sorry, I accidentally hit the stop button instead of the pause. So this is going to be in two videos. So our next half is on probabilities with events that are not mutually exclusive. So if A and B are not mutually exclusive events, then you have the probability of A or B would be the probability of A plus the probability of B minus the probability of A and B. And we do this so that we don't overcount. So don't want to double count. And a good way of looking at this is we have red cards as our red circle and face cards as our blue or purple circle. And you know that there's a section in the middle that are red king, or we can even do it king of hearts, king of hearts, king of diamonds, queen of hearts, queen of diamonds, jack of hearts, jack of diamonds. And you know, if you were counting red cards, you counted all of those because those are all red cards. And if you counted face cards, you counted all of those because they're also face cards. But by doing that, we added them twice into this. So this way, we don't double count. We subtract it out once. So that way, we only count it one time. So our first example on this one is if a person is randomly selected from the population represented in the table, find the probability that the person is married or female. So we have the probability of married or female equals the probability of married plus the probability of female. Are these mutually exclusive? Could you, if you're married, can you not be female? No, we have a lot of people who are female who are married. So we cannot double count, so we have to subtract the probability of married females. So we have the probability of married. So married group down here. So 130 over our total. And notice here we have our total, 242, plus the probability of female. So total female right here, 124 over 242. Subtracting the total of married females. And you see you have the married column and the female column, and where that overlaps is right here. So minus 65, 242. That's 189 over 242, which appears to be 0.78 or 78%. So 0.78 is our probability. So our next one's try it yourself. It has its own table. I can take a second and draw it. That's probably going to be my better option. I was just going to have you guys look on your own page. But if you give me a minute, I'll do my best to make it quick. Okay. Well, this is lovely, I can tell. 1, 2, 3, 4, 5, 6. 2. Okay, so we'll do male. Well, I drew too many columns anyway, so excellent. Okay. I know this is super exciting to watch. So Air Force, Army, Marine Corps, Navy, total, male, female, female, total. Okay, so 370, 370, 420, 80, 500, 170, 10, 180, 320, 60, 380, 120, 1,210, 220, 143. So again, notice that this changed here, if you do have your notes, because that does not add up to 60. That was a typo. So we want to find here, based on the problem that you have, if one person is randomly selected from the U.S. military, find the probability that this person is in the Army or is a woman. So probability of Army or woman equals the probability of Army plus the probability of being female. Can you be in the Army and be female? Yes. So probability of Army and female. So probability of being in the Army. Okay, so that's going to be 500 over our total. So here that's going to be 500 over 1,430 plus, okay, the probability of being female, 210 or 220 over our total. So 220 for 1,430 minus the probability of female and in the Army. So we have our two columns that happen, female and in the Army, and where those two meet is at 80. That's where it's double counted. So minus 80 for 130 for 1,430, which gives me 640 over 1,430. Let's put that into my calculator. Maybe 640 divided by 1,430. That gives me 0.4475. So approximately 0.448 or 44.8%. Okay, so that was your try it yourself. Let's go on to our last group. Okay, so and probabilities with independent events. If two events are independent, if the occurrence of either of them has no effect on the probability of the other. So two things that occur and they don't have an effect on the next one. So if I flipped a coin, if I got a heads, it does not mean the next one is more likely to have a heads because I already got a heads. They're independent. They're not going to have any effect on the next one. Okay, so here's our example. Find the probability of family of having 4 boys in a row. So the probability of having 4 boys in a row. So what's the probability of having a boy? It ends up being just slightly more than 50%, but for all practical purposes, we still consider it to be 50%. It's actually just a little bit less. The probability of having a girl is just a little bit higher. So your first child, the probability of it being a boy, 1/2. Now that you had a boy, does that increase the odds of you having a boy or decreasing them? No. The next time you have a child, you have the same probability, 1/2. And then your third child, you don't know. It's going to have 1/2 probability of being a boy. And then the fourth child, they're all have no effect on the one that comes after it or before it. So you end up multiplying these together and you end up with 1/16 of probability of having 4 boys. We're going to build on this one and then do our try it yourself. Try it yourself. Should just abbreviate that all the time. So what's the probability here of having 9 girls in a row? Well, we know the probability of having a first girl is 1/2. The probability of having a second girl is 1/2. Third, fourth, fifth, sixth, seventh, 8th, and 9th. Let me make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 girls in a row. And then we can figure this out by 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2, I'm going to get out my calculator. 256 times 2 is 512. So 1/512 is the probability of having 9 girls in a row. Okay, guys, this is it. The end of this section. So I will assign some homework. Let me know if you have questions. Good luck.